Hello, my structural analysis friends. Today's lesson, we'll be talking about the ASCE minimum design building loads for impact loads and for live load reduction, two significantly more advanced topics than what we've talked about in the past and that come with a lot of assumptions that we'll need to discuss. So without further ado, we'll get ourselves going. So the first topic that we'll talk about is our impact loads and the way that the ASCE 710 attempts to deal with those. Okay, this is located in section 4.6, and I've copied part of that text for you just so we can kind of reference back to what it's saying. Impact is a load that has some form of energy when it hits a structure, or that it imparts into a structure. Now, it could be, like a projectile hitting a structure, or it could be caused by, any sort of moving machinery or motors or something that are, being power driven, that will exert force, usually in a cyclic behavior, but not always into a particular structural form. Now, impact is very complex. Without getting into structural dynamics, it's very hard to analyze, logistically how machinery or impact is affecting a particular structure. Structural dynamics says that vibration and impact response are related to not only the mass of the structure, but also the stiffness of the structure. So a steel beam will behave differently than a concrete beam when the same load is applied to it in some sort of vibration or moving pattern. And so there's a lot of assumptions that have to take place. It's very involved and mathematically intensive to come up with the true form. So to help us solve this, ASCE 710 has some smaller subsections and some assumptions that they based off of practical experience and practical theory, and those are what we're going to focus on for this series. Okay, maybe when we do a structural dynamics seminar or calculations, we'll come back around and try to address this in a little bit more detail, but for most engineers that are doing normal everyday structures and nothing special, nothing unique, okay, or earth-changing in this case, I guess just your standard run-of-the-mill type structure, these will give you a good first guess as to the increased loads that are needed based off of object, okay? So for impact, like we said, this is located in section 4.6 of the ASCE 710. You'll see that up at the top on the notes, okay? But it also correlates back to IBC 2015, and that'll be in 1607.9 is where you find that. And the way that the ASCE code handles impact is they basically break things down into, is it a light machinery or is it a heavy machinery? So you've got to kind of watch pretty closely the wording of the machinery types, and those are what we're looking at is, is it a printing press or, an aggregate screen or, some sort of, motor driven device that's causing these vibrations or these impacts in the floors. Okay, you'll notice that elevators would definitely be a machine that meets that standard, but those are designed according to a different standard. So to get into those, you'll have to go find the ASME A17.1 provisions for that, okay? Because not only are they designed for impact loads, but they're also designed for explicit deflection limits, okay? And we'll talk a little bit more about deflection limits in a later video, but elevators are kind of a special animal, okay? Especially because a lot of times they're involving humans, okay? And that there are humans associated with those particular machines, whereas the machines that we're looking at would be, like I say, some sort of industrial equipment or something like that, all right? So the way that impact is handled is that the industrial machine is split up between whether they're classifying it as a light machine or some sort of reciprocating or power-driven unit. Okay, so for a light machine, okay, which it could either be shaft or motor-driven, okay, they're going to require a 20% increase to the live load. So if you know that your live load that's being put out by this machine is 40 pounds per square foot, you're going to increase that 20%, and then the one that you're going to run your models for these pseudostatic loads for impact would be 48. That would be a 28% increase of that, okay? Whereas if it's a heavy machine, which is some sort of reciprocating machine or a power-driven unit, 2,000 RPM or something just very, very, very large, okay? And again, they leave a lot of this up to interpretation. Well, I mean, what do you do if you're kind of in between the two? you have to use your engineering judgment to understand the type of machine that you think you need to be designing for. What lets you sleep at night as you start to do this? Okay, now that being said, recognize that there is a 30% increase between light and heavy. So the heavy, if it's a reciprocating machine or a power-driven unit, they're going to increase at 50%. Okay, and that's just, again, because and what they're worried about with this, okay, these power-driven or these reciprocating machines is that resonance effect that we've talked about a little bit, okay, in which, as you deflect things, the deflections get bigger and bigger and bigger and bigger, but that's because of the cyclic nature. Because where we talked about earlier on the structural response being related to its mass and its stiffness, okay, there's also another factor that is the frequency of the force that's being applied, okay, and something special happens if that frequency of the force starts to match that ratio of mass and stiffness, okay, or the natural frequency, okay. Now, again, that's not the true formula for natural frequency, but those are the factors that are involved, okay. And so, depending on that, if those two numbers start to kind of, converge to a singular unit on there, then what happens is deflections go crazy and start to expand. Technically they could go to infinity, but obviously structures have material limits, okay. And so that's the thing that they're looking for, and that's why they have this bigger increase on these reciprocating machines, because the reciprocating machine has a common frequency that's happening with what they call the forcing function, okay, or the frequency of the force that's being applied from the machinery, okay. And so that's all they're doing for impact. Now, like I say, there's a lot more to this, but just so that we have kind of a sense of how much we're going to increase, we're going to be either increasing 20% or we're going to be increasing 50%, okay. And again, it is up to the engineer and manufacturer's judgment. Technically, you could increase those percentages. If I knew I was hitting that special resonant frequency, 50% might not even be enough for us to design for. So anyway, that will cover us for impact. Our next up will be then live load reductions. Our next section involves the concept of live load reduction. And live load reduction is broken up into two different subsets. Okay, one is for floor reductions and the other is for roof related reductions. So what a live load reduction is, if you remember, we defined live load in an earlier video as being kind of a load that is non-stationary or has some variability associated with it, that it can move in or out, okay, that it's based on time of day or just the nature of the loading, it comes and goes, okay. Now again, live load does not include things like wind or snow or something like that. This is typically most often associated with people loads. So what we look at is, remember that there was, some statistics kind of behind the formulation of all of those numerical values, okay? Now, for, say, a residential section or a classroom, we always said that a live load is typically taken as about 40 pounds per square foot, and maybe the hallway outside was 80. What happens with live load reduction is that because they're based on probability, we have to kind of look at things a little bit differently, okay? And so I'm going to pull up in a kind of a small example here. And so suppose that we have, a live load reduction that is set up between floor and roof, okay? And let's just say that we're looking at 40 PSF. Now I know it's uncommon to get 40 on the roof, but let's just say there's 40 on either one of these areas. If the area of my room or where this load is being applied is something fairly small, in this case it's a 10 foot by 10 foot area, maybe it's a closet or a very, very tiny bedroom or something like this, the likelihood of seeing 40 pounds per square foot in this entire area is pretty large, right? Because remember, we said, if we just take kind of a token, 1 square foot area, the probability of loading all of those 1 foot square areas in this 10 by 10 area could be pretty reasonable, okay? Whereas if this area is 40 feet by 40 feet, and the probability that I load up all of these at the same time with that same load is significant. The likelihood of that happening is a lot less. This room is a lot bigger, and suppose that that you have 20 people that you're fitting in this room. I mean, we're not worried about fire safety standards or anything like that. But getting 20 people into this room, they're pretty well packed wall to wall. Whereas here, maybe they're located over here, maybe they're over here. They all kind of move around, they congregate, something. But the odds of fully loading this whole area are very, very small. Okay, and so what live load reduction is an attempt to kind of use some statistical basis to say, all right, we don't need to design this for as much of this 40 pounds per square foot load as we might this guy. Okay, now again, it's still 40 pounds per square foot is the base. It's just that we're going to reduce it based on the probability of actually loading this entire area. Okay, now, if this is, some sort of meeting area or it's a storage facility, there are some limits on when you're allowed to reduce and how much you're allowed to reduce. And that's the nature of what we're going to cover in this part of the video. All right, so, even if it gets to, say it was 400 feet by 400 feet, now it's even smaller likelihood. So there's a correlation that exists between the area that's being loaded and the likelihood of that area seeing all of this load. And that's what the nature of these reductions are trying to do. All right, so let's talk a little bit about what the ASE 17 code sets up as a prescription for it, okay? So what they've done, and we're going to start over on 4.7.2, okay? There are two formulas that are associated with it, okay? You've got the US units, which is the top one. That's the one we'll focus on in this class, but if you want the SI equivalent, there's the one below. Notice that all that really changes is this numerical factor up in the head of this thing, okay? And that's kind of has to do with the conversion between AT, and we'll define what AT is here in just a moment, okay? The only parameters that it takes to define this is you have to know what your initial, this L naught live load was, and I need to know a KLL parameter and an AT parameter. Now, AT we're going to use a lot here in the coming days, okay? And this is known as the tributary area. It's the load that's associated with a particular member, and we'll kind of define those here in just a second. All right, KLL has to do with kind of the nature of the structural piece itself. Is it a primary member? Is it a secondary? Primary members being that if a primary member is damaged or removed from a structure, you have huge structural implications, whereas a secondary member will have, maybe you'll have a localized failure of the structure, but the rest of the structure is still standing. So think of, like if you lose a column, that's a primary member because big portions of your building will come down. Whereas if you lose just, a simple joist beam, between two girders on one part of a floor, maybe you lose that part of the floor, but the rest of the structure typically will probably survive. Okay, that's what these factors are trying to account for. All right, so what happens is that this KLL parameter, which is this live load element factor, you can find those in table 4.2. Okay, and they're basically, like I say, they're broken down into different types of members. So if you are at an interior column, okay, if we come back to our picture, that would be a column that's located in the interior of the region, something like that over here. Okay, so this would be an interior column. Okay, this would be an exterior column. Okay, and so that would be a different factor. So if you're at an interior column, if you look at it, if I lose one of these, the damage to the building will be significantly more than if I lose one of these exteriors, right? And that has to do with, let's just put a few more columns around the border here. We've got kind of a regular framing pattern. Something kind of like that. That if I lost this corner column, you can see that based off of tributary areas, he's kind of responsible just for that portion of the structure, right? This guy takes that piece, this guy takes a whole lot, and this guy takes a piece there, okay? But realistically, all of the load that's here, and it's not exactly like this, but it tends to want to go to the nearest column, okay? Whereas if I go to an interior column, and take this as my shaded region, all of this load tends to want to go to this column. Okay, now again, this is an idealized approach, and we'll talk more about these tributary areas. But that's why you can see that an interior column typically has a whole lot more area associated with it than these exterior. Okay, now the shaded region I've showed here, this is the AT value. Okay, so what it does is it takes basically half of the distance between this direction and half the distance between this, and says this guy will cover half of it. That they're all working equally. Now, again, there are some assumptions that have taken place. We've assumed that the columns are in the structure are all about the same size, that one isn't massively oversized compared to the others. Just normal structural type of thoughts are occurring here, okay? And so that's how we're kind of start to calculate these AT values. Okay, so based off of that area, the shaded region that we're talking about, and then these KLL factors that we're going to show in these tables, you can see that an interior column has a KLL of 4, okay? An exterior column, and this is without cantilever slabs, meaning there's no slab hanging over it that gives it extra load, is also a 4. Okay, with cantilever slabs, it gets a 3, and so forth and so on. You can see that interior beams, so if we look at our shape, this would be considered as an interior beam, a member that connects those two columns, okay? And then even get a few girders laid into our building here. Let's just say that we're taking this beam here in the middle. Okay, that would be an interior beam. Okay, whereas this might be an edge beam over here. So this is an interior. Okay, and this is an edge. Okay, so what happens with tributary areas on this, because typically there are multiple beams running in the framing of this thing, that if this is, let's just draw another dark one in here. Okay, then the tributary area associated with this guy would be that little portion there. It's half of him to his neighbor and half of on both sides, both directions. Okay, whereas for a girder, like say maybe this guy, so let me pull this down a little bit. And I'm using squares just to kind of represent my girders. Let's look at tributary areas associated with this guy. And again, we've got a whole bunch of framing that could be happening where this girder is holding up a bunch of members. If I'm looking at this piece, we would call that as a girder. All right, and his tributary area is that any load that's out here, the load goes from the slab into the joist, and then a little bit goes this way and a little bit goes towards each direction, that he becomes responsible for half of the area between him and his next parallel neighbor. All right, so that would be his tributary area. And you can see that girder gets a whole lot more tributary area because it's collecting load from a whole lot more, a larger number of beams that are sitting on it. Okay, so you can see that even though they're kind of in the same floor area, the area associated with this little sub beam is not nearly as much as what's happening to the shaded area on this girder, right? And that should make sense, right? Because if I lose this little guy, the rest of this floor is still safe. But if I lose that girder for some reason, now we've got a real problem that all of these floors come down, okay? And so that's why this area associated with the member, this tributary area, is such an important, crucial idea as we start to kind of look at the loads. Okay, all right, so with that being said, we're pretty much we've defined our parameters for the live load element factors and as well as the tributary areas. Okay, there are some limits that are set forth in what's allowed, or how small can you go, because if we go back and look at our formula here, you can see that AT is in the bottom. So if I had an infinitely large area, I could knock this term out completely. Okay, well, they say that, and if I do that, then you're down to a fourth of the load of what you originally had. Okay, well, what's the magic number for AT? Okay, and we'll talk about that here in just a second. Okay, so there is, while we're allowed to reduce, we can't get too overexcited and over-reduce it, take it too far down, because I can get to a load that's just not practical. So what kind of values are we looking at? And that's where we're kind of headed with all of this. All right, so anyway, you've got these two tables, or this table for the KL factors, you've got the equation to work with. We're in pretty good shape for that. Okay, all right, now, the limit I have on this note is box, okay? Obviously, it's not box in the code, but I pointed out this is where that limit is set, okay? So L shall not be less than 0.5 L naught, so half of L naught for members supporting one floor, and L shall not be less than 0.4 L naught for members supporting two or more floors. Now, for most beams and girders, you're bounded by this 50% limit, but if it's a column on a multi-story building, in which maybe I'm coming and I'm, beautiful quick drawings, right? Comes down and does something kind of like that. Well, then the column that's right here, while we talked about in the last picture, in an earlier picture, that for each floor he was associated with a portion of the area on the floor, if I go look at, a column, this guy is affected by not only the load on the floor that he's holding up, but he's also being affected by the floor on the load of all the floors above him. Okay, and so that's how we kind of look at it. And that's what they mean by multi-stories, okay? Because all this load is coming into this column, and then that load is coming down, and this is building up. And so, as you get higher up in the structure, under the roof, you only have one floor. But for all the other floors, like especially for this guy, I would have the effect of the floor above him and the floor above that, or all the floors, if this is a high-rise building, a multi-story building. And that's what we're talking about by these multi-story objects. Okay, but they're all still kind of tying back to probability. So for that multi-story column, you're limited to 40%. Okay, because again, they're saying, well, I may load up one floor, but what are the odds that I load up both floors in the case of that sketch that we just made? Okay, so kind of just to summarize what we've just said on this, okay, single story reduction is limited to 50%, multi-stories are limited to 40%. Okay, beams and girders typically only support one story. Girders, depending on how they're loaded, may support one or multiple stories. It kind of depends on, do I have a column coming down? Let's go back to this picture. Okay, let's say that this is the girder and that we're framing things something like this. That if my building is something like that, then this guy is only supporting his own floor. But if there were a column coming down here and not one below it, now he's holding up multiple floors. Okay, and so that's why they say a girder can sometimes, in certain circumstances, hold up multiple stories. Okay, now most normal construction, typically, especially in small 3 or 4 story buildings, typically they're running columns all the way down. But again, not always. And so that's why we got to be kind of have an understanding of how the load is flowing through this building when it comes to tributary area. Okay, so that's what we're talking about, why a girder can fall into both single story and multi-story approaches. Okay, columns, okay, almost always are supporting multi-story structures. Okay, now one other restriction that you haven't seen in that note is that live loads that are greater than 100 pounds per square foot may not be reduced. Okay, these are considered high occupancy loads. These are your meeting areas, conference rooms, warehouses, libraries, all sorts of storage facilities that they will not let you reduce it because of the nature. These numbers are so large. But if you're dealing with an office building or you're dealing with a residence that's 40 pounds per square foot or 50 pounds per square foot, you're allowed to reduce those. Okay, all right. Let's see. Okay. All right, now, I do need to point out one last little tidbit that I forgot to say, and I apologize for that. Okay, how do we know what the limit is to being able to reduce? And that shows up in this upper paragraph up here. This has got a little bit of a glare. There we go. Okay, basically, if the product of KLL times AT is 400 feet squared, or 37.16 meters squared, you are permitted to reduce the load. Okay, so if you have a beam that's very short, say, or a column that has 100 square foot tributary area and it's an interior column, in that case you would hit that 400 number exactly. Okay, but again, AT is the area of those shaded regions that we were showing you in these. Okay, so again, this whole area associated with this girder that we looked at over here, that's AT. Okay, so if this was 10 feet and this was 10 feet and this is, say, 30 feet that way, my AT is 10 plus 10 times 30 would be 600 feet squared. Okay, my KLL for that interior girder, if you will, which would be coming over to this table, we would be looking at, see, an interior beam. His KLL is 2. Then KLL AT then is going to be 2 times, 600 would be 1,200 feet squared. Okay, that's greater than 400 feet squared. Therefore, our reduction is allowed. And then I could go in and I could start to reduce the number based off of this, and just plug into the formula, and you would get your percentage number. Okay, so the original design, if this was an office, maybe it's 50 pounds per square foot. Okay, that's the L naught. Right, so if we just work a real quick example here, this would be L naught, okay, times 0.25 plus 15 over square root of KLL AT. This would then be 50 pounds per square foot times 0.25 plus 15 over the square root of 1,200. All right, I'm going to pause it. I got my calculator here. Didn't have that handy with me. Sorry about that. That's it. All right, I'm back. So this would be 50 pounds per square foot multiplied by a coefficient of 0.683 Okay, so if I multiply that, this would be multiplied by 50, 34.1 would be what you would design that girder for, okay, based off of the tributary reductions. Now again, we have to look at the limit. This number is greater than 50%, so then we're okay for our limit, because here's my L. My L minimum that you have to design for is 50 PSF times 0.5 for one floor, okay, would then be 25 pounds per square foot is the minimum that would be required. So if I went crazy on the area and dropped this thing, maybe it was a lot bigger building, then if this number was, say, 28%, then I would be bounded by that limit. Okay, but we're still above the minimum, but that's why you got to check both. So this is what I would model my structure on, would be 34.1 for a roof or for a floor live load reduction scenario. Right? Okay, so anyway, that was kind of a crude example, whipped up on the fly, so I hope that made sense to you. Okay, all right. The next piece then that we're going to look at has to do with, get to the right page here. Okay, has to do with roof live loads. Okay, they're kind of the same way, but they're done a little bit differently. They have a little bit of a different setup to them because of some logical reasoning that happens on. Okay, so the typical value for a roof live load is 20 pounds per square foot. Now remember, we separated roof live loads from regular live loads because normally in most structures, roofs are restricted access. Okay, this 20 pounds per square foot accounts for maintenance workers up there, the occasional tree limb that falls down onto the roof and sits up there, or pile up of leaves, or whatever the case may be. It's just a little bit of this kind of extra load, but it's not the 40 or 50 that you saw in a residence or an office building, right? Because I don't need that much up there, okay? Okay, and basically these roof live loads are a minimal load applied to structures without ordinary access. Now, by ordinary access, we mean that it takes some effort to get onto the roof of a building. Now, again, people can get on the roofs. I recognize that, but if you don't have a staircase going up to the roof, that it's a ladder that you're climbing, or there's a lock on the hatch that gets you to the roof, it's pretty safe to call that unrestricted access. Okay, so if it's difficult to gain access to, LR is 20 pounds per square foot is sufficient, okay, for our limits. But if not, if you have a staircase that goes up to it, if it has an observation deck, then I'm using the normal live loads associated with, okay? And that's kind of what I'm trying to say here. If a roof can be accessed by a staircase directly, regardless of whether a door or hatch is locked, don't use the 20 pounds per square foot. If it's got a door on it, or a staircase going to it, I use a normal design floor load on it. Right? Because at some point, somebody's going to go up there and say, hey, this is a great place to work, or a great place to sunbathe, or whatever, and then they're there, and then all of their friends start coming over. And so again, engineering judgment on how the harder it is to get on the roof. If you've got to scale a ladder, yeah, it's pretty hard to get on there. But if it's, if not, well, then you got to kind of consider it that way. All right. Okay. So now for roof live loads, it's done in a very similar fashion. It's just that the formula is a little bit different. Okay. And so the reduction in our roof live loads, okay, are done in accordance with this. Okay. Now roofs are broken down into flat, pitched, and curved roofs. Okay, and the formula has a section that looks something like this. Okay, LR is L naught times R1, R2, and these factors are given then over here. Okay, and then for SI units, it's still the same formula, but your limits. Okay, now you'll notice that the limits on the roof live load, you can reduce those between the range of 12 and 20. Okay, so most of the time, most structures, I just call it 20 and I'm done. Okay, I just take the upper bound limit on that thing. But, if you had a very large area, maybe it's a warehouse or a distribution facility or something, then it might be worth your while to sharpen your pencil. But generally speaking, that's not a huge swing on this. You're starting out at 20 anyway on an upper end. Okay, but that's where we're getting into. And like I say, if you have access to the roof, and other people, and it's not getting this 20 pounds per square foot minimum, you're not using this formula anyway. You're using the old floor live load scenario as well. Okay, now, so the factors that we have, okay, so for R1, it's kind of a step function, if you will. It's 1.0 when AT is less than 200 square feet. It's 1.2 minus 0.001 times AT. So AT is that tributary area associated with the member that you're trying to reduce the load on. Okay, And you'll notice that that's between 200 and 600 square feet. Okay, and then 0.6 for anything greater than 600. Okay, and then for the R2 factor, then what this is kind of a slope factor, if you will. You've got the area relationship, but then you also get the scenario of if my roof looks something kind of like this, okay, for fairly flat roofs, what we're defining is this is 12 and this is F. Okay, that's the F coefficient, the number of inches per foot that the roof rises. So if you're looking at a very, very flat roof, F is a very, 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 very small number associated with that. It doesn't even look pitched at all, but you kind of get the idea. Whereas if F is very, very peaked, and the way I kind of remember the effect of the roof factor is if I put something on here on a steep roof, it has more of a tendency to fall than if I put one here, right? That this guy isn't going to move or be relocated based on the pitch of the roof. Okay, now this will be an important concept when we get to snow design here in a couple of lessons, that the steeper the roof, the less the snow load, all right? You think about, the ski chalets in the Swiss Alps, right? They always had a roof structure that had a slope of like 70 degrees. Whereas most normal residences in the U.S., we're looking at more like a 4 on 12. Okay, would be a normal pitched roof. Okay, for our associate, and that I think that corresponds to like 37 degrees or something along that would be kind of a normal everyday roof. Okay, now again, it depends on what your structure is. If it's something unique, then you have unique loads on it. But normal run of the mill, those are the values that we're looking at. Okay, all right. But that's what R2 is attempting to capture, is that sloped roof, and that's this formula here. So again, if F is less than 4, this is considered as a flat roof. 1.2 minus 0.05 F is for 4 to 12. So a 12 on 12, that's up to 45 degrees. 4 on 12 is, like I say, more like 30 degrees. Okay, and then 0.6 for anything that's steeper than that. Okay, and then once you have that, it's just a matter of plugging into your formulas. Pretty straightforward. Okay, right. And so I'll show you this. This is what we just talked about. Just kind of wrote it out a little bit more clearly, hopefully. Okay, in general, the design loading on roofs comes from snow. However, in areas where snow is not extreme, maybe you're in the tropics or, southern Florida where not a lot of snow, then the minimum prescribed roof live load can often be the controlling factor, and that's why we have to look at it. But like I say, if you're living in the Upper Peninsula of Michigan, the roof live load isn't the problem. It's the snow that's going to be the controlling factor. But you have to check both. You have to check all, right? Because you never know when that building's going to get up and leave Michigan and move to Florida, right? Sorry, that's a joke. All right, so okay, so we have our unreduced live load. That's the L naught. That was our 20 that we were looking at. Okay, and then these are the factors that we just talked about. Okay, one thing to point out: this is AT less than 200 foot squared. Remember when we did the floor beams, it was KLAT. Okay, so the KL was used based on the type. Remember, for roof, it's not. It's just a pure area calculation, right? So be very take notice that KL is not used in these roof reductions. Okay, and then the R2 factor, which is the pitch roof. Okay, again, we said this was the flat roof one. Okay, this is if it's reasonably shallow, and this is for very steep roofs for those factors. Then you just plug and check and do everything the exact same way that we did before. Okay, all right, so I hope that kind of helps explain kind of how area reductions are set up for you. I'm trying to see, I think that's all for today. I hope that it's kind of clarified, kind of how the calculations are done and the lower limits that are set. Okay. Again, they're not overly difficult, and in a pinch, for if you need to, you can reduce the loads to sharpen up your building. But if I'm doing a preliminary analysis, a lot of times I don't even run the reduction numbers, not until later on, until I'm sure, because if you have a layout and you do all your reduction numbers and then somebody changes the geometry or your column centers move, then all of your area calculations are affected. And so this is normally something I look at on the back end kind of as a check, but as you get more experience, you get a little faster at it, and you get more of a sense of when it's going to be a problem and when it's not. Okay, for most normally framed structures with columns that are 40 feet on center, you'll end up reducing a fair amount of load. Okay, if it's an interior beam, typically beams are 4 foot on center. It's 40 foot long. That's 160 square feet. It's an interior beam. Multiply that by 4. Yeah, you're reducing that guy. Okay, in columns, you're definitely reducing. But so you've got to kind of watch the limits. But if you get into really, really small structures, then you can't even reduce anyway. Okay, so again, all of this ties back to probability as we start to kind of look at it there. So anyway, I guess that will do it. So we will see you guys next time. If the video is helping you out at all, leave us a like down below, leave us some comments if you got any questions, and we will see you guys on the next go around. Have a wonderful afternoon. Happy engineering.